All right, so we're going to pick up kind of where we left off yesterday. Um, in our notes yesterday, we were kind of talking about what logarithmic equations look like, what their graphs look like. And so we're going to kind of switch gears now and talk about the same kind of functions. They act very similarly to what we talked about yesterday, but they're dealing with this base e. All right, now we just watched a video over what E is. But if you're maybe watching this video on your own, you were in class to like watch that video of E. I did put a link to that YouTube video that I showed on the calendar for today. So if you just go to the Schoology, go to the calendar, and then you just click on that video. It's like less than 2 minutes, and it is a really kind of a nice job of introducing why we use E, like what it is in math, why we use it. It's not just some random number that we decided to just make up and just start using one day. Okay, so if you want to kind of get a little bit of background information about E, I would suggest that you go and watch that video. But so we're still going to be graphing these like we did exponential functions yesterday, but E is going to be representing this number that is approximately 2.72. Okay, it shows up a lot when we're dealing with compound interest, when we're dealing with certain situations in like biology or physics, chemistry, like where things are multiplying at a specific rate. E can be used to kind of describe that. What we're going to kind of look at today is how we would graph this again, like yesterday with tables. So I'm going to go ahead and just sketch a table here. And again, you can use a calculator to help you do this. So if you go to your calculator and you hit your table button, we're going to type this in. Now to find E on your calculator, let's see. If you find it before I do, let me know. You're going to hit your second button, and then 2 buttons below that where it says LN, there's the little in green E to the X. You're going to do that. And so you can then hit that button. It should automatically pop an E in there, and then it's going to have the exponent box for you. And so we just need to type in an X, and then you can hit enter. And then let's still just go from -2 to +2. So let's start at -2, and let's look at our points here. Okay, so at -2, again, I'm going to use my decimals here, and I'm going to round. This is 0.14. -1 is at 0.37. 0 is at 1. 1 is at 2.72. And 2 is at 7.39. Okay, and you could round to the nearest tenth too. You don't have to do 2 decimal points out like I did. But you can see how these numbers are kind of behaving the same way that they did when we just had like a regular exponential function. The only difference is that the numbers maybe aren't going to have whole numbers show up except for maybe at 0. Okay, but let's go ahead and graph this over here. Again, I'm going to just kind of zoom in because this graph gets so small. It's kind of hard to see where you're supposed to put the points. So we had -2 was just above 0, really small. -1 is very similar. 0 is at 1. 1 is at about 2.7. Again, I'm estimating, and 2 was up at about 7.4. Then again, I'm going to connect these these points. So it should look like that. As you can see, it looks really similar to the graphs that we saw yesterday. All right. What would be the asymptote here? Good. It would be y equals 0 still, because it's never going to cross that x-axis. It's never going to be y equals 0 on your table. Like we could go up or down to positive or negative, and you're never going to get a 0 there. What would be the domain? What are your x values? Good. It's going to be -infinity to +infinity. And what would be your range? Good. 0 to positive infinity. Very good. So you can kind of see this looks a lot like what we talked about yesterday. It's just that your base is changing to, instead of like 3 raised to the x power, we're now dealing with this base of e. Okay, and we'll see a little bit later too, e showing up in some of those types of situations that we talked about in that video that went over like why we even have the number e. Okay, now just like we did with those functions yesterday, let's talk about what happens if we start to do some transformations to it. Again, kind of think about this one that we did up here as kind of like your parent graph. And so we're going to start changing a couple of things, and then we want to see what does that do to our graph. All right. So if we look at this first one here, what is this going to do to your graph movement wise? What's going to happen here? Good. That +3 is going to make it go right 3. So I'm just going to write that up here. So all those points that we had from this up here are all going to go to the right 3. Okay. So I'm just going to come down here. And I'm just going to start at 0, 1, because I know that's a really easy point for me to graph. And then it's going to go right 3. So you're going to be at this point here. Because I was at 0, 1. Now I'm just going to go right 1, 2, 3. So now I'm at 3, 1 instead. Okay, then if we keep going, 1 was at about 2.7. So again, I'm just going to go right 1, 2, 3. And then 2 was at about 7.4. 1, 2, 3 to the right goes there. And then you can kind of get an idea of where the other one should go. Again, you could look at those points that we had on the parent graph and just shift them all right 3. Okay. Did it change anything about the asymptote, the domain, or the range? No, those are all the same as they were, right? So I'm going to go ahead over here and just say my asymptote is still y equals 0. My domain is still negative infinity to positive infinity. And my range is still 0 to positive infinity. All of that did not change. It's unaffected by the fact that it moved right 3. Okay, what happens on the next one? Yeah, the -2 is going to cause us to go down 2. Good. So let's go ahead and graph that. Now, again, my original point was at 0, 1, so I'm going to go down 2. And then 1 was at 2.7. I'm going to go down 2. And then same with the other points. So it should look something like that. Okay. So over here, what would you guys say for your asymptote now? Good, because it went down 2, that means that your asymptote is going to have to reflect that. So we would have y equals -2 instead of it being 0, because it's clearly crossing the axis this time, but it seems to kind of flatten out there again as it approaches that -2 on the y-axis. Okay, what about my domain? Is that changing at all? Good. No, my domain would still just be negative to positive infinity. Those are just my x values. How would we rewrite our range, though, now that the graph shifted down? Yeah, it'd be -2, 0, right? Or not 0, I'm sorry, infinity. Okay, nothing below -2 is allowed. Okay, so that just changes that asymptote a little bit. All right, why don't you guys take a minute here and try to do the last one on your own. Okay, I went ahead and graphed mine so you can kind of see how it compares to yours. What movements happened here? Good, it went right 3 and it went down 2. So again, it's kind of the combination of the two things that we just saw. What is your asymptote at? Good, -2. Your domain? Good, negative to positive infinity. And then what would be your range? Good, still -2 to infinity. Very good. All right, any questions on how we would graph something with the E? All right, if you guys go to the last page of this section here, we're going to switch gears a little bit. We're not going to be graphing anymore. We're going to talk about something called compound interest, okay? And so compound interest is one of those examples that they mentioned in that video about what E is maybe used for or why it's kind of an important number. And so compound interest formulas use that E value in it to help you evaluate like how much money is going to be in your account after a certain time period. For a compound interest formula, T is going to represent time, but it's always measured in years. So if they're talking about half a year, or if they say something like quarterly or monthly, we'll have to think about how much of a year that would be representing. Okay, so like if they're doing something monthly, how much of a year does 1 month represent? Okay, capital A is going to be like your ending balance. So what do you end up with after the compounding of the interest has been done? Capital B is going to stand, P is going to stand for your principal, which would be like the amount that was put into your account. R is going to be your interest rate. And something that I just want to make sure you guys are aware of here is that when you have a rate, that's going to be a percentage, you need to always convert your percent to a decimal. Okay, so make sure that you do that. Don't ever leave your rate as a whole number or a fraction. Make sure that you're converting it to a decimal, or you're going to get numbers that are way, way off. Okay, N is then going to be representing compounding periods in a year. So like how many times in a single year did it get compounded? So if they say like annually, semi-annually, quarter annually, like those kind of things would tell you how many different times it was done. All right, so there are two different formulas that we can use. One of them is for compounding periods, and one of them is compounded continuously. So they are a little bit different. So when they're giving you a problem, you'll want to make sure that you read through the information that they give you to know, should we be using compounding periods formula or should we be using compounded continually? Usually it'll say somewhere in the problem which one they're talking about. Like they'll use the word continuous, or they'll talk about a specific period of time that they're compounding, and that'll kind of be your clue as to which formula to use. Okay, so let's do an example here. It says that a sum of $10,000 is invested at an annual rate of 8%. Find the balance in the account after 5 years subject to quarterly compounding. They're first asking which formula should we use here. Now, if we kind of go over this, we've got this $10,000 is going to be your P. Okay, so I'm just going to put a capital P above that. 8% is going to be your rate, but remember, we're going to have to convert that to a decimal. How do we convert a percentage to a decimal? You got to divide by 100, so that should be 0.08 for your rate. Okay, then it says find the balance in the account after 5 years. That's going to be your time. So 5 is going to be your little t. And then let's see what this last piece says. It says it's quarterly compounding. Quarterly would be like a period of time. Okay, so that would be the same thing if they said like monthly or weekly, like those kinds of things would be keywords to look for when they're talking about compounding periods. Now, quarterly, if you think about a whole year, how many quarters would be in a year? There'd be 4, right? Okay, so this quarterly means that it's going to be 4, and that's what's going to go in for your N. So the formula I want to use is this one right here. Okay, so capital A is equal to capital P times 1 plus R over N, and then N times the T. Now I'm just going to plug in all the pieces that we identified. So we're trying to find the ending balance. We put $10,000 in, so that's going to go in for your P. We said our rate was 0.08. And we said n was 4, so that's got to be used here, and it's got to be used up here in our exponent, and we said t was 5. All right, now there's kind of a lot going on with this formula, so if I were you and you're trying to maybe calculate this, I would take it like chunk by chunk. You can type all of this in at one time. You just got to be really, really careful. If you're going to do that, I would suggest that you put in parentheses, just like how it's written right here, so that your calculator reads it correctly. If you miss parentheses or you don't put parentheses in, it's probably going to calculate it incorrectly for you, okay? So I'm going to kind of walk you through what I would do. So if you just want to kind of follow along, I'm going to start on the inside of the parentheses there. I'm going to take 0.08. I'm going to divide that by 4. I'm going to add that to 1 now. Okay, so I'm at 1.02. That's kind of inside my parentheses. Now that's going to be raised to this power of 4 times 5. What is 4 times 5? 20, right? So I'm going to raise it to the 20th power. Okay, so I've got some wild, crazy decimal here. And then I'm going to take it times that 10,000. And I get, we're talking about money here, so $14,859. And then cents, I'm going to round it, 47 cents. Okay, so this is how much would be in that account if the interest was compounded quarterly. Okay, again, I just want to talk about what that means when they say that something interest is like money you're earning on the money just kind of sitting there in this account. Okay, so you're not doing anything to the money, you're not adding anything in, you're not taking anything out, it's just kind of sitting there doing its thing. All right, now if it's quarterly compounded, that means that 4 times a year, they look at the balance that you have in that account, okay? And you're putting interest based on that. So they're taking the amount that's in the account, they're adding that 8% interest to it for you, okay? Then the next quarter comes around, they do the same thing again. So you're making money on the money that's just sitting there, all right? So after 5 years, this is how much should be in that account after it's had chances to compound like that, all right? Now, the next example here, it's still kind of talking about this, but let's just look at how this is worded. Everything about this is the same until the end. It still says the sum of $10,000 is invested at an annual rate of 8%. Find the balance in the account after 5 years, subject to continuous compounding. See how they threw that word continuous in there? Okay, so this is a little bit different than when what we were just doing with it being compounded quarterly. Okay, so I'm going to use the second formula, which says A equals P, and this is where E comes in, and E is raised to the R times the T. All right, so let's plug this in. We still don't know what A is. That's what we're trying to find. What did we say P was? Good, that's still 10,000. Now, E is going to be raised to our rate, which is still what? Good, 0.08. And then T, how many years? 5. Very good. All right, now this is a little bit simpler in your calculator. Again, though, if you really want to make sure you're typing it in right, you could start with the E stuff first. So in the exponent, take 0.08 times 5, and then take that times 10,000. This time for an answer, we get 14,918 and 25 cents if I round it here. Okay, there's one last little follow-up question. Which bank is better? What is the difference in the accounts? So if you're looking at these two amounts, which one would you want to put your money in if you wanted to get more? Yeah, the second one, right? Because it's got more money in it after. So I would say the second bank. Okay, and if they're saying what is the difference in the accounts, well, let's just subtract. Let's take 14,918.25 and let's subtract 14,859.47. Looks like it's a difference of 58.78. So not a huge difference, but you know, if I want my money to do the most growth, I'd probably want to put it in that second bank. All right. Any questions there on E or compound interest formulas?